So let's talk about 2:1 compressor. So the 2:1 compressor, I can consider it to be partial product 1, 0 and partial product 1. So there are 2 bits. It can be easily represented as an AND and an OR operation here, and then the summation of that. And if I look into the AND operation here, the P0 itself will be 1 by 4. P1, the probability of P1 will be itself be 1 by 4 because it's a partial product, right? So the Xi being 1 is the probability of Xi being 1 is 0.5. The probability of Yi or Yj being 1 is 0.5. So the probability of P of P0 is 1 by 4. The probability of P0 and with that of P1 will be actually be 1 by 16. And probability of P0 plus P1 will be nothing but 7 by 16. And that is something we can get from this particular truth table. So remember that if I have this kind of a probability, then in fact, if I can, can I avoid this completely in my summation process, because it will have an error of only 1 by 16. Right? So what we said was the summation of the partial product, that is what we are interested in. The summation of the partial products can also be rewritten as the summation of the OR products and then the AND products. In the AND products, the probability of this being 1 is actually 1 by 16. So most of the cases it will be 0. So in that sense, if I actually ignore it, then if I do only the OR operation, it will actually have, it can reduce the computation. Right, so the AND product is kind of ignored. Can we ignore that? And what happens to the approximate sum? So one such truth table is given: P1, P0, W1 is given. W1 is nothing but P0 plus P1 is considered to be the W1. And then the sum is given. And then the approximate sum is given. This is the accurate sum. So if I have 0, 0, it is 0. Approximate is also 0. If I have 0, 1, I will have the sum as 1. 1, 0, it will be 1. 1, 1, it will be nothing but 2. But whereas my approximate sum will give me the same values except this particular value. So the error here is 1, and then the probability of error is nothing but 1 by 16. Right, coming straight from this particular value. Right, so what we have done is in a 2:1 compressor, instead of the regular sum, right, 2:1 compressor is nothing but a half adder. Instead of an XOR gate, why not represent just with an OR gate? Right, going ahead, 3:2 compressor, can we now approximate 3:2 compressor? Of course, we can do that. So summation of the partial products, 3 partial products will be involved. And in this case, and if I consider P0 and P1 as 2 of the partial products, I can rewrite it as P0 and P1 and P0 or P1 and leave that P2 as it is. And now if I actually do P0, P1, use this and this, further use it as AND and OR recoding. So I will have P0, P1, P2 and then P0, P1 plus P2, and then this one will be our last stage. Right. So finally, I need to evaluate what is the probability of this particular being 1 and what is the probability of this being 1 and this being 1. Turns out that this is nothing but 1 by 4, 1 by 4, 1 by 4, 1 by 64. So we can easily ignore this. So the approximate sum for the approximate 3:2 compressors, we can actually have as nothing but the summation of only these two partial products. So what is that? P0, P1 or that of P2 and P0 plus P1. Right, so instead of 3:2 compressors will be nothing but a full adder, and so instead of 2 XOR gates, what we can do is we can have an OR gate here. We can have so we can have an OR gate here, and then we can have an AND gate here. Right, so this will give me the partial products. So P0, P1 plus P2, comma P0 plus P1, and eventually get a W2, W1. So if I actually use see in the truth table here. So W2 and W1 are actually, and in the diagram here, W2 and W1 can be generated by AND and OR gates. And in the truth table, we can see that the approximate sum and then the expected sum, most of them are matching, except the last case here, which is expecting 3, and the approximate one is giving the answer of 2. Right, so this one, once we get this W2, W1, we can actually do the summation of that. Which will give me an approximate 2 here, summation of that, and it will give me an approximation of 2 that. So here also we can actually use an XOR gate, or we can use an AND and OR recoded adder. So we can similarly extend it into 4:2 compressors also. So we had got 3:2 compressors. So 4:2 compressors will have 4 partial products, and we can consider 2 each, P0, P1, and an OR recoding we can apply here. So P0, P1, P0 plus P1, and P2, P3, and P2 plus P3. And once we have all these things, so we can actually do this with this. So P0, P1, comma P2 plus P3 will be nothing but ANDed, and then OR, and then similarly P0, P1 with that of P2, P3, so AND and OR. So eventually we'll find it out that this is 1 by 64, and then this is 1 by 64, this is 1 by 64, 1 by 64, we ignore that. So finally, I think we can approximate it into this particular AND and OR recoded forms. So we can ignore this, we can ignore this. So finally we'll be left with P0, P1 plus P2 plus P3, and P2, P3 plus P0 plus P1. So with W2, W1, so we can use it, we can form this using the AND and OR gates. So similarly, we can do the 5:3 and 62:3 compressors also. So eventually, by having 5 partial products, we can have 3 of them, and for having 6 of the partial products, we can eventually reduce it further. So you can see that it is actually having the 3 of the on the outputs here. Right. So what we have tried here to design is we have approximated the compressors, and compressors are actually used for adding up, finally counting the number of ones in the partial products, and finally giving us the multiplier. So if we are approximating the compressors, we are naturally going to get the approximate multipliers. Right, so the higher order approximate multipliers, what we have said is generalizing everything. So 7:4, 8:4, 9:5, 10:5 can also be designed by extending the earlier explained method. But to keep it very, very simple, we can also say that 7:4 could be realized using 2 of the lower order compressors, and 8/4 could be realized by having 2 of the 4/2 compressors, 4:2 compressors. So what we'll do is we'll restrict ourselves to a lower order compressors, and then try to use, apply that into the multiplier design and get the inaccurate results. So this is what we'll be doing. So this is the kind of a very generic, simple algorithm we'll be using for assigning the compressors. So this is nothing but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12-bit cross 12-bit multiplier. So overall, I will have 24 columns. So this is 24 columns. And the length here will be nothing but 12. So the first partial product generation stage will have 12. And for approximating, what we will do is the LSP side, the lower bit side. So in the 16 columns, or in the 24 columns, the 12-bit columns, the starting 12 columns will be the approximate compressors, and the last 12 columns will be the exact compressors. Right, here I think we'll be using the approximate one, but rest of the cases it is the exact compressors. And we will do the partial product reduction stage and then go to the next stage. In the next stage also, we will see that we will apply the approximate compressors to an extent where the height is maximum. So here the height was maximum here, right? So we divided the LSP side, we divided the region 2 segments, and then applied on one segment we applied approximate compressors, on the other side we applied the exact compressors. Here also, once we get this get into the second partial product reduction stage, we'll identify the maximum height here, and once we get the maximum height here, we will apply up till that particular maximum height we're going to apply the approximate compressors, and lower than that we're going to apply the accurate compressors, and finally we'll keep on reducing the number of stages, right? So here is the overall design of an 8 by 8 cross 8 bit multiplier, And this is our the regular data multiplier, which uses the half adder and full adder, right? Doesn't use any 4:2 compressors or 5:2 compressors. So it uses only half adder and full adder. So it is much more an accurate design, and here it is an approximate design. The approximation here is done is because on the LSP side we have approximated the compressors itself, and on the MSP side there is an exact compressors. But while it is kind of reduced from here to here, you can still see that maximum height on right of the maximum height, everything is in approximate compressors. Left of that, it is the exact compressors, and then so on. So the data multiplier actually has the sequences of from here to here, from here to here, from here to here, and then finally this one, and then the fast adders. This one 8:8 bit multiplier with approximate compressors is giving us one reduced stage, and then from one reduced stage to the next reduced stage, and then we can directly achieve the fast adders. Right. So comparing with that of the data multiplier here, I think this is much more efficient in terms of hardware because the number of stages has been reduced. Right. So the sequence or the reduction stages, reduction steps for an 8x8 bit multiplier of that data multiplier type, it is 8 to 6 to 4, 3, and 2. So the number of full adders that has to be used is 35, half adders it is 7. Approximate, I've written not without truncation, I'll come to that later. So the approximate multipliers which we have used here is 8 to 4 and then 3 to 2. So there is a the number of stages, the reduction stages has drastically reduced, and the approximate compressors that has been utilized is 14. All right, moving ahead, so this is a 16 cross 16 bit multiplier design, and this is the data multiplier design, right, using the half adders and full adders. And then note here, there's a sequence here of reduction. Here the sequence of reduction is very, very simple. So 1, 2, 3, 4, 5, 6, 7. So there are 7 stages here. Here it is only 4 stages. The number of approximate compressors is 55 here. Here the full adders and half adders are 195 and 15. Here it is only 27 and 3. Right. So remember that what we have done is, we have applied onto the LSP side, we have applied the approximate compressors, and on the MSP side we have applied the exact compressors, right? And then we have applied, just to understand or the see the impact of on the application side. This particular approximate compressor driven multiplier design is actually used for the Gaussian smoothing application. So Gaussian smoothing application is one of the very regularly or very frequently used filtering method. Just to looking at the Gaussian shape here, it gives us a kind of a blurring. It applies a blurring on top of that particular on that particular pixel values. So in this particular case, if I consider this as an original image here, and if I apply the Gaussian smoothing here on top of this, I'm likely to get some kind of a blurred image, and kind of this blurring image is actually very, very useful in some of the filtering process, right? So one of the heavily used image processing application, right? So in this particular Gaussian smoothing application, the multipliers are a more frequently used arithmetic operators. And instead of using an exact multiplier, if we use the approximate multipliers, how does it behave? So this particular slide talks about applying the approximate multiplier in the Gaussian smoothing filter, and what is the output of that. So if I have an original image of a cameraman original image, and if you use if you build the Gaussian smoothing the filter using the exact or the data 8-bit multiplier here, this is what the image it looks like. It is compared to the original image, it looks a little bit blurred, and that's what we want. That is what we expect from the Gaussian smoothing filter. And this particular output on the right side is from the Gaussian smoothing filter, when the filter is actually developed from this approximate 8-bit multiplier. Right. So if I actually compare between these two images, there is hardly any difference. Only thing you can see is there is little bit of the data is kind of lost, but I think all the prolific information or all the relevant information which is kind of the image is rendering is still present, right? So with respect to these two images, we still get the same kind of information that is required. So that's why we say that the approximate computing is used especially for some of the error resilient applications, and image processing happens to be one of them. To find to find the statistical difference between these two images, one is the output of the exact multiplier, and then one is the output of the approximate multiplier. There is something called as a structural similarity index. That's a parameter which quantifies how much of the output is kind of degraded. So if I consider the output of the exact multiplier, so this particular image, and if we find out what is the SSIM value, structural similarity index, turns out to be, this is what the benchmark is. So that's why it is SSIM is 100%. And if I find out the SSIM for this approximate 8-bit multiplier, which is kind of adopted in the building the Gaussian smoothing filter, the output of this is giving us around 98.88%. Right, so this is what we are getting, the SSIM, the structural similarity index value. So if I can find out the difference, quantifiably or statistically, it is only a degradation of around 1.12%, which is very, very small. So this particular image is about, after running the output image into the SSIM module function, we will get this particular image, and from this particular image we will be able to calculate or estimate the SSIM value, right? So if I consider the SSIM function on the output of the Gaussian smoothing, I will likely to get one particular image which rounds about 200%. And the SSIM of this particular output image turns out to be like this, and this is giving us around 98.88% of SSIM. Right. So this is the overall output of the images, right, using the 8-bit multiplier and then the 16-bit multiplier using the approximate compressors. Right. And here I have different types here. I have said 1-step full, 1-step truncated, 2-step full, and 2-step truncated, right? So I need to go back to the 16-bit designs or the 8-bit designs and then try to explain what does that 1-bit and 2-bit represents, right? 1-step full and 2-step full, right? So in this sense, in this particular the partial products stages, or the representation of the partial product and its reduction stages, one step full represents. So we are applying the approximate compressors only on the first stage, right? Only on the first step, and then from the second step onwards, there is no approximate compressors at all. So that becomes 1 step. And it would be applied for an 8-bit multiplication or a 16-bit multiplication. Thus 2-step, full represents, we are applying the approximate compressors on both the stages, not only in the first stage reduction, but also in the second stage reduction, which will go into the third stage. Right. So we will have 2-stage or the 2-step where we will apply the approximate compressors. Right. There is one more term called as the truncation. Right, truncation represents that in this the lower LSB side, everything is truncated to 0. Only we are considering only about the MSB side, the higher order significant bits. Right, so the first 8 bits will truncate it to 0. So whatever is the partial product, we will, for a 16 cross 16 bit, the first 8 bits for first 8 columns will all be truncated to 0, because we know that even if we make this the LSB side 0, the MSB sides will still be have more weightage. So we can easily do the exact compressors or the approximate compressors and get the values, get the product values. But having truncating the lower LSB side is not going to have that much of a difference in the values between the inaccurate results and then the exact results, right? So that is what is called as the truncation. Right, so we're having this for an 8-bit and then a 16-bit, we can actually have 1 step without truncation, 2-step approximate compressors without truncation, 1 step approximate compressors with truncation, 2-step approximate compressors with truncation. So I can actually do it for 8-bit multiplier as well as in 16-bit multiplier. And in the end, we'll actually get 4 designs for an 8-bit and 4 designs for the 16-bit. So this particular row is for the 16-bit multiplier, and this particular row is for the 8-bit multiplier. And the 8-bit multiplier, you can easily see that the SSIM value turns out to be 99%, 99%, 98%, 98%. When for the 1-step, if I apply the approximate compressors without doing the truncation, this will be the highest. If I apply the truncation, it will be slightly less than that of the previous value. 2-step, if I apply the approximate compressors, it will go down to 98%. 2-step application of the approximate compressors along with the truncation will give me 98%, even lower than this, right? If I use the 16-bit and do the 2-step full and then 3-step full, right? So instead of in the 16x16-bit, it's not only the first stage, second stage, but also third stage is available because the higher number of columns are there. And then the length is also higher. So it will eventually reduce it to, we can easily apply the approximate compressors even to the third stage. So in that particular case, if I have 2-step, full means 2-step, 2 stages where we'll apply the approximate compressors, we will get the SSIM value as 0.99. But if I have the truncation in a 16-bit multiplier, there is a significant loss here, right? So 2-step, 2-stage truncation is not good, whereas a 3-stage, applying the approximate compressors is still better. 98% of the SSIM value is achieved. But 3-step, again with the truncation, making the LSP part to be completely 0, it also degrades very, very low, right? So in this particular lecture, what we had seen is how do we do an approximate compressors using an AND and OR recoding, and then actually neglecting the part which has a very less probability of being 1. And then use that for putting the approximate compressors and use that particular approximate compressors into the multiplier design. And we have seen the 8x8-bit, 16x16-bit multiplier design, and then if those multiplier designs, if we use it in a Gaussian smoothing application, what will be its impact, right? Its impact in terms of the SSIM is not it is almost close to the 100%. It is giving us the results of 99 and 98%. But overall, the area, the footprint of the design of the multipliers on the chip, the power consumption for the 8-bit or the 16-bit approximate multipliers, as well as the delay, the critical path reduces significantly. So all this could be leveraged without causing much of an SSIM degradation in the final application side.